Good day everybody, in this video I will talk about liquefaction resistance of sand and I will explain how we can estimate resistance factor. So let's look at some example. We're going to look at soil profile, which is here. We have 12 meters of medium sand, and after that we have another 8 meters of fine sand. And we're also given data from SPT tests, so this is N values. So this is what we need to get from site investigation so that we can estimate the liquefaction resistance factor. And in the end, we're going to arrive at this plot. I already prepared it and I will explain how we get it. So this is the factor. You see that this is 1, and everything that is less than 1, it's not going to be good. So that means that this soil, this sand, will have a very high susceptibility to liquefaction. Everything is that on the right hand side, which means that most likely this soil is not going to liquefy if there is earthquake. So how do we get this factor FL? So this is the formula, and I'm going to explain the procedure which was introduced by Iwasaki and his colleagues. So this is simplified procedure. It's a little bit old, 1981. I believe it was adjusted a little bit later, but for this particular tutorial, I think this procedure will be the best, and I will explain how it works. So we'll start with the safety factor, or we'll call a resistance factor to liquefaction. You see that this is the ratio between R and L. So R is the in situ resistance to earthquake loading, and the L is this cyclic loading that induced by earthquake. So what we want to see is that if the load induced by earthquake it's very high or it's low, and then we just compare it to the resistance of sand, and most likely it's going to be sand or maybe some gravelly material, but usually it's not clay because clay doesn't liquefy. So this is a formula how to get R. So, and this is the formula how to get L. So let's start with the R. So this is the in situ resistance. You see this is actually two formulas, 1 and 2. They're based on the empirical correlations. And for this, to choose which one we're going to use, we need to look at this value, which is called D50. I'm not sure if you've seen my videos about grain size distribution. So if you haven't done it, I will put a link in the description of this video. Please watch it. So you will see that to get D50, you need to know grain size distribution curve of the material. So this is percentage finer, and this will be size in millimeters. Usually we're going to get curve like this. So this is 100%, this is 0. Then we're going to get 50%, and then see what 50% correlates, what value it correlates with the size in millimeters. So this is how we get this value D50. And for this example, I chose these two values. They're not very different, but it will guide us. It will show us what formula to use. We're going to use this one, equation number 1, because D50 is 0.31 for the first sand, and for the second sand it's 0.11, so it's within this range. So this is the formula we're going to use. If you do some investigation of the material and you find that D50 is different, then you also can look at this range, and if it's within this range, you're going to use this equation. Okay, so we know that for this example that I've already selected for us today, we're going to use this equation. And now let's estimate the L. So L, I'm not sure if you've seen another video that I've done. It's on the SIS procedure, simplified procedure, how to estimate the liquefaction potential of sand. I will also put a link in the description. So this is kind of a similar formula to that. What we need to know is the acceleration. that will be generated by the earthquake. So we're going to look at the maximum acceleration, and you will see that in this case maximum acceleration is given in gals. I think it's a little bit old-fashioned. I think now when you look at the data, they use G's. So you can see, for example, that they will say maximum acceleration will be, I don't know, 0.18 g or 0.32 g, right? So they don't use gals, but if for some reason you're gonna see it here that you know that you need to change g, which is acceleration of gravity, to this value of 980 gals. I will show later. We're going to look at this example. Another important thing is that we need to consider pore water pressure, and we'll consider pore water pressure through this effective stress. Here, effective stress. If you remember, effective stress is total stress minus pore water pressure. So pore water pressure is very important. If there is no water, if there is no pore water pressure, there won't be liquefaction. And in this case, you will see that we have pore water pressure here, groundwater level at 1 meter. So that will generate pore water pressure during earthquake loading. And another important factor is this R, which is called the reduction factor. The idea is if there is liquefaction that is supposed to happen, it typically would happen in the top part of the soil profile, so like probably somewhere here. It's very rare when liquefaction occurs at deeper depths. It's because the stresses are much higher there. So from our experience, from many cases, you will see that liquefaction happens in the top maybe 4 or 5 meters. And this reduction factor will just put emphasis on the top part of the soil profile. So you see that this value RD will actually decrease when soil profile goes down. And again, I will show you how we do that. So before we go to the next slide, I just want to also mention that when we look at SPT data here, we already have some idea where liquefaction may happen, because for liquefaction to happen, that material that is going to liquefy, that is sand or gravelly material, sandy gravel, it should be loose. So if it's loose, it's going to have a relatively low value of SPT. So in this case, SPT N values, you see that here maybe up to 6-7 meters, the values are pretty low, especially at the depth of 6 meters. I think SPT value is only 2, which means that this material sand is very loose and weak. And if we look here at the data, you will see that this resistance factor, it's less than 1 at the depth of first 6 meters. Okay, now I'm going to explain how I get this graph, and we'll do this example together. I'm going to the next slide. Okay, now let's do some calculations. So this is the data that I already showed you. So this comes from site investigation, and as already mentioned, we'll look at D50 for both sands, and we're going to use that first formula to estimate resistance. And these are my calculations. So I did it in Excel, and I think it might be a little bit easier to do it in Excel. And this is the values that we're going to get in the end. This is L and R resistance, and this is this factor against liquefaction. So I'm going to explain this row, this depth. We need to do the same procedure for each depth for which we have SPT N values. So this is SPT N values. So, and this is the depth. So for each value, we're going to repeat the procedure, and we're going to get this value of FL. So as I mentioned, we're going to do this one. It's just example. What you can do later, you can practice and check your data against my results. So let's start with the value of R resistance. So the formula will be 0.0882 times N value. Here we have effective vertical stress divided by 98 plus 0.7 and plus 0.225 multiplied by logarithm with base of 10, and here we have 0.35 divided by d50. So what do you know d50? d50 will be this one. Sorry, because we're gonna do this part, d50 will be this one. So d50 it's this value, 0.11. So because we're doing for the second layer of sand, which is fine sand, we need to get effective stress. So this one value we still don't know. Let's calculate the effective stress. We're gonna start, because this example it's a little bit simplified. You will see that what I did, I put unit weight the same because it will be easy for me to calculate. Most likely when you actually go through soil profile of 20 meters, you will have layers of sand or sandy material with a different unit weight. So in this case, you just need to consider it. In this example, it's simplified. I just made it a little bit easy for myself. So in this case, we will just say that unit weight is depth, which is which one though? 16.3 meters, right? We're doing for this depth, and multiply by the unit weight, which is going to be 16 for the whole soil layer. That will give us 260.8 kilonewton per square meters, or kPa. So now we're going to calculate water pressure. So, well, I hope you know how to do it. If not, just watch my videos how to do water pressure. So we know that there is groundwater level at 1 meter below the surface. So that will be the distance here. So that will be, I can write it's 16.3. That's from the surface minus 1 meter, because groundwater level starts from 1 meter below the surface, and multiply by the unit weight of water, 9.81. That will give us value of 150 times 0.9 kPa, and effective stress, it's total stress minus water pressure, should give us 110.7 kPa. So let's see here, we have 260 in this table, yes, and effective stress 110.7. Okay, so let's also estimate the value of RD. We're going to use it to estimate the load from the earthquake. So in this case, it will be using the formula 1 minus 0.015 times the depth. The depth is 16.3 meters, and that will give us value of 0.755. Okay, so what we will do now is we are gonna calculate the value of R. So I'm going to rewrite the formula again here and show the values I put in. 0.0882 square root of n. So for this depth, n value is 35 divided by effective vertical stress, we just found 110.7 divided by 98 plus 0.7, and we're continuing. The next component is 0.225 logarithm with a base of 10, 0.35 divided by the d50, it's what is the value of d50? 0.11. It's this one, right? So according to my calculations, it's gonna give us value of 0.499. Yeah, should be about this value. So the one that you see here, it's from Excel. So when you do hand calculations, you will see that may be a little bit slightly different, because it depends how much you round the values that you obtain. Okay, so now let's get the value of L for the same depth. So as already mentioned that, or maybe I didn't mention it, the earthquake that we're going to design against, we're going to have a maximum acceleration of 170 gals. So you can go back to the previous slide and see it's there written at the bottom. So we're going to divide by the G. In this case, it's 980. Then we are going to have the ratio between total stress, 260.8, and the effective stress, which is 110.7. And we're going to multiply by the reduction factor, which we already found. It's 0.755. And that will approximately give us value of 0.308. So now if we estimate the value of FL, it will be R divided by L, so it's resistance against the driving force, 0.499 divided by 0.309. That will give us approximately 1.62. So this is the number. So if it's greater than 1, this means that sand at this depth most likely is not going to liquefy if there is earthquake with a maximum acceleration of 170 gals. Okay, so this is just how to calculate these values. You can practice by yourself, look at the data, and let's go to the next slides. I have a little bit of more explanation to do. So in these slides, that's the values we obtained. So we just got this value, and that value was 1.62. So this is 1.62. So the whole procedure, the one that we've done just right now, we're going to use to get another value, which is very important for liquefaction hazard assessment. So this is called liquefaction potential index, and this was also introduced by the authors of this procedure. So this is the formula how we're going to get it. In this formula for this particular index, we're going to look at the whole depth, and you will see that we're going to integrate through the whole depth of the soil profile from 0 to 20 meters. So it doesn't matter if you have all 20 meters of sand, or you have maybe sand, then you have clay, then you have sand and rock. You're still going to do it for 20 meters. It's because this procedure was developed for several cases that took place in Japan, and when they analyzed those cases, there was 20 meters of sandy, sometimes even silty material. So they came up with this procedure. They said, let's look at the first 20 meters, but it doesn't really matter, because whatever we're going to see, it's typically in the top few meters of the surface. So if we look at our data that we just obtained for this soil profile, you will see that up to this level, the safety factor, or not safety factor, factor against liquefaction, it's less than 1, which means that most likely the sand is going to liquefy. So what we just want to see it, how thick the soil profile, the one that is going to liquefy, and then we're going to estimate it. So sometimes we have only a very thin layer of sand that may liquefy during earthquake, and the rest of the soil profile is going to be stable. So if it's maybe only 15-20 centimeters of sand, that may be not as dangerous as, let's say, 4 or 5 meters of sandy material that is going to liquefy. And this liquefaction potential index will actually define what we call potential, or it will show how thick and how susceptible that soil mass is to liquefaction. And let's just do this example, calculate this index for this soil profile. We're going to use the formula. So in this case, we're going to use F, and F is 1 minus FL. So FL, it's the values that we just obtained. So that's resistance to liquefaction. So if this value 1 minus FL, it's less than 1. So in this case, we're going to keep F as it is. If it's going to be more than 1, so in this case, we are going to assign 0. If FL more than 1, so we're going to assign 0. So in other words, if we look at these values where we have FL greater than 1, we're going to assign F as 0. So for these cases when we have FL less than 1, F is going to be 1 minus FL. Right? Okay, so for this example, I chose depth 6 meters. Again, we have to do it for each depth, and we will have to sum up the numbers. So for 6 meters, we see that the value of FL, it's less than 1. It's less than 1 FL, which means that F is going to be equal 1 minus FL, and that will be 1 minus 0.39 will give us a value of 0.61. So that's the number. So again, we're going to put more emphasis to the top part of the soil profile, and we're going to introduce this function W that will change with the depth. So this is how it works. That's the formula. So let's use this calculate W for 6 meters. That will be 10 minus 0.5 times the depth. Depth is 6 meters. That will give us value of 7. So that's value of 7. So now we're gonna multiply these two values, and we're gonna have it's gonna be value of 4.25. Okay, I'm gonna write it here for 6 meters. So F times W for 6 meters, that's 0.61 times 7. That will give us value of 4.25. So now we're going to sum up all these numbers. So you see that everything here I assign 0 because value of FL is more than 1. So everything is going to be 0. So this means most likely not going to liquefy. Now let's calculate the index PL. It will be 2.18 plus 1.37 plus 4.25 plus 0.37 and plus 0.09. That will give us approximately 8.26. Okay, what I'm going to do with this number? So with this number, we're going to look at this classification chart and see where it is. So this value falls in the range from 5 to 15, which means that liquefaction risk is high. So we'll need to do something about that side. So maybe some measures to prevent liquefaction or to mitigate it. If we are in this area, we get PL is 0 or from 0 to 5. So in this case, liquefaction risk is relatively low. Usually we don't need to do anything. So, but when this value of potential liquefaction potential index increases, this means that the risk to earthquake and the liquefaction will also increase, and we need to do something about it. Well, that's it for today. So there is lots of theory. So hopefully that was useful for you. Have a nice day and bye.